Okay, let's talk about something we all have, but maybe don't think about enough: our circulatory system. We kind of picture it as, a bunch of pipes and a pump. But what if I told you it's actually this mind-blowing engineering marvel? One that's constantly solving some of the most complex problems you can imagine, every single second, without you even noticing.
I mean, just think about the scale of it all. Your body is made of trillions of cells, and every single one is like a tiny little client that needs nonstop service. They need deliveries, oxygen, nutrients, and they need trash pickup for their waste. How on earth do you run a logistics operation with trillions of customers?
Well, the answer is that your circulatory system is an absolute master problem solver. It has perfected 5 key engineering challenges that keep this whole massive operation running like clockwork. And today, we're going to walk through exactly how it pulls this incredible feat off.
So here's our roadmap. We're going to look at the pure physics of how to move blood efficiently. Then we'll get to the whole point of the journey, the exchange. After that, we'll see how the system cleverly matches resources to demand, how it controls pressure so nothing goes wrong, and finally, how it gets everything back to the start to do it all over again. Let's jump in.
First up, the efficiency problem. Your body has literally tens of thousands of miles of blood vessels. How in the world do you push a fluid through a network that vast without wasting a ton of energy? Well, it all comes down to mastering the physics of flow.
The ideal situation, right, the absolute gold standard that your body is constantly shooting for, is something called laminar flow. Just picture it: smooth, parallel layers of blood just gliding past each other. The blood right in the center moves the fastest, and the layers closer to the wall of the vessel are a bit slower because of friction. It's clean, it's orderly, and it is incredibly efficient.
And you can really see the difference here. On the left, you've got that perfect, low-resistance laminar flow. But on the right, that's its chaotic cousin, turbulent flow. This mess happens when things get disrupted, maybe at a fork in an artery or a narrowed spot. The flow gets all jumbled up, and that creates more resistance, which makes the heart have to work a whole lot harder.
And get this isn't just some abstract idea on a slide. That turbulence can actually create a sound, a whooshing noise that a doctor can hear with a stethoscope. It's called a bruit. And it's a real, physical clue that something, like plaque, is blocking the vessel and messing up that smooth, efficient flow. It's the body literally telling you there's a problem.
So, we've figured out how the blood moves so efficiently. But why? Why is it moving in the first place? This brings us to the next massive challenge: the logistics problem. What is the ultimate point of this entire incredible journey?
And this, right here, is the whole reason for the system's existence. All those major arteries, all that pressure, that perfect laminar flow, it all leads to this single moment: the great exchange that happens in the tiniest of vessels, the capillaries. This is where the real magic happens.
The mission itself is a pretty straightforward 3-step process. Step 1 is delivery. Drop off the goods, like oxygen and all the nutrients, from the blood to the tissues that need them. Step 2, pickup. Grab all the trash, the waste products like carbon dioxide. And finally, step 3, disposal. Carry all that waste away so the body can get rid of it. Everything else is just in service of this fundamental exchange.
Okay, but here's the thing. This system has to be smart. It has to be dynamic. Your body's needs are always changing. This leads us to our third big problem, the resource allocation problem. How does the system know where to send blood and when?
Just think about it. You decide to go for a run. All of a sudden, your leg muscles are screaming for more oxygen, more fuel, right now. Meanwhile, your stomach doesn't really need to be digesting lunch at that exact moment. The circulatory system needs a way to redirect all that traffic, and it has to do it fast.
And the secret is the peripheral circulation. This is the vast network of smaller arteries and veins that acts like the body's own intelligent delivery grid. Its most critical job is to match blood flow to what the tissues demand. It can open up vessels to flood an area with blood, or it can pinch them off to send that blood somewhere else. It even works as a storage tank, just holding on to blood until it's needed in a more active part of the body. Pretty smart, huh?
All right, so we're managing flow, we're making deliveries, but this whole operation is happening under pressure. And that brings us to the fourth big challenge: the safety problem. How does the system keep enough pressure to get the job done without, blowing a gasket?
So what is the perfect pressure? Well, it's not just one simple number. It's actually this incredibly delicate balancing act with really dangerous consequences if you get it wrong.
I mean, if the pressure gets too high, you risk damaging the fragile walls of your blood vessels over time. But if the pressure drops too low, then your vital organs aren't going to get the steady supply of blood and nutrients they absolutely need to function. It's like a constant tightrope walk between two very bad outcomes.
And that's the body's relentless 24/7 goal, to constantly monitor and tweak that pressure, keeping it right in that sweet spot where everything works. It's a nonstop feedback loop that makes sure the whole system can run safely and effectively.
We've delivered the goods, we've managed the pressure, but there is one last, absolutely critical piece to this puzzle, the return problem. After the blood has made its delivery, it's at really low pressure. So how does it get all the way back to the heart to start the whole trip all over again?
Well, this process is called venous return. It's the often forgotten but absolutely essential second half of the whole circulation loop. It's the entire job of getting that deoxygenated blood back home to the heart so it can be topped up with oxygen and sent back out on another mission.
And here's the bottom line. Think about it. A pump with no fluid is just a noisy box, right? It's completely useless. The heart can beat all at once, but if blood isn't being efficiently returned to it, then the amount of blood it can pump out drops, and the whole system just grinds to a halt. Venous return is absolutely non-negotiable.
So, when you put it all together, from mastering the physics of flow, to that great exchange in the capillaries, to smartly directing resources, managing system-wide pressure, and ensuring the final return journey, you start to see that your circulatory system isn't just a bunch of tubes. It's a dynamic, brilliant, and totally silent masterpiece of problem solving.
It really makes you wonder, doesn't it? What other incredibly complex, perfectly designed systems are quietly working away inside of you, solving impossible problems every single second, just to keep you going?